So opening to page 26, we'll just make a couple of quick announcements. So first of all, the quiz from last class, which became a take-home, is now officially due. Throw it into the folders. Also, project number 8 is officially assigned, so grab a copy of it. It's on your table. Project 8 is due on May the 3rd. What day is that? Is that a Friday? May 3rd is Friday. So 1 week from today, project number 8 is due. Project number 8 is the last math project for this semester. Project 9 is the reflection one. So this is the last real math project you'll have to do. It is due 1 week from today. And by the end of today, you should be prepared to answer all the questions on this project. All right? So today we talk about power series. The next 3 classes after today, we talk about Taylor series, then our review day, then our test. Any questions on the schedule? We're getting there, yeah. So the test is on the 8th. Is that Wednesday? So a week from this coming Wednesday is our 3rd test. Okay, so we begin here on page 26. And 26 talks about this thing called a power series. So it's a brand new definition. Hopefully you read about it last night. So a power series is just some function of this form. You've got a constant plus another constant times x minus some number. That's kind of weird. Plus another constant times x minus the number squared, plus a constant times x minus the number cubed. So this a is the same in every one of these guys. The constants in the front can change, but the a is always the same, and the variable is x, and in theory could go forever. So you can write it in summation notation like that. And so the idea is, for example, something like number 4. You guys can see the increasing powers on the x, right? X squared, x cubed, x to the 4th. How much is the a, since I don't see x minus anything? It's 0, right? So it could have been like x minus 1 cubed and x minus 1 to the 4th and x minus 1 squared. But it's just x cubed and x to the 4th. So the a apparently is 0 in this example. How much is the first constant by itself? That's the 1. How much is the second constant? It's 1/5. And the third one is 1 over 25. Okay? So you can think of this kind of thing as a polynomial with infinitely many terms, which is kind of strange. Or you could think of it as a function whose value at x is obtained by evaluating a series involving x. So for example, if I asked you guys to plug in x equals 2, just making up a number, then that would be an infinite series. It would just be numbers, right? 1 plus 2/5 plus, what's the next term? 4/25 plus 8 over 125 plus ... So it's a function, right? F of x equals this thing. If I just plug in x equals 2, I get a brand new series, an entire series, and maybe this series converges or maybe it diverges. And if I plug in x equals 2.1, I will get a different series. So I can think of it as a function where in order to figure out what the output is, I have to do an entire series calculation. Okay, so let's look at number 3 here. We'll go with Dawn. Okay, so I just want to give like a little sneak preview of what's coming in the next 3 classes. So I made this yesterday in GeoGebra. It took about 2 minutes to make this. What function is that? Sine looks like the sine function. Does it go through the right starting point on the y-axis? Yeah, it goes through the origin. What's the max? Max looks like 1, min, -1. That all looks good. What should the first positive x-intercept be? Should be a pi. Does it look like it's a pi? Where should the end of the first positive period be? Should be a 2 pi. Does that look right? All right, and then the next one could be 3 pi over, or 5 pi over 2, I guess. All right, so it's sine. So so let's just keep dragging. Where should the next x-intercept be? This one here was at 2 pi at the end of this cycle. Next one should be at 4 pi, which is about how much? 12 and change, right? All right, so we're just going to drag this in a little bit here. So we're expecting the next cycle is there at 12, and that looks like, oopsies, just want it to go away. Okay, so that looks good, right? So everybody's convinced this is sine graph? Not the sine graph, which is quite strange because it looks an awful lot like the sine graph for a while. So this graph is actually not the sine graph at all. This is a polynomial. What kind of degree polynomial would go up on the right and down on the left? Something odd. This is an odd degree polynomial. I will show you this polynomial in all her glory. So there's part of it. So it's x minus x cubed over, that's 6, plus x to the 5th over 120 minus x to the 7th over, I think that's 5040. And then it goes on. So let's see, I think I can show you more of it. So, okay, there it goes. So x to the 29th is the highest power. It makes sense that it's odd. You guys said it was going to be odd. So somehow that crazy polynomial there, the 29-degree polynomial, acts an awful lot like the sine graph for a while, and then does the normal odd degree polynomial thing. So this is where we're headed. And this crazy polynomial is an example of the kind of thing that we're talking about here, where you just keep adding higher and higher powers of x, okay? All right, so that's a sneak preview. We'll get there next class. So let's take a look at number 4. Ernie.
Consider the power series 1 plus x over 5 through zero 1 series. What kind of series is this? How would you rate this series closed form?
Okay, so I'm saying what kind of series, so it must have a name. So first of all, the fact that there are x's involved means it is called a power series. So if you see x's to all those powers, that's our definition of a power series. But we had special series. We had the harmonic series. Is that the harmonic series? No. We had p series. Is that a p series? No. Anybody recognize what kind? That's a geometric series because there's the same multiplier every time. So it is geometric. And if we wanted to, we could write it in closed form, meaning this with the sigma notation. So how are we going to write, like what's the basic pattern here? What's the general term look like? So I'm going to write a fraction because I see a fraction. Yeah, so Ernie says 1/5 to the n. Dawn said x to the, what'd you say? X over 5 to the n. Sorry, I wrote a 5 up there. Ernie, I think you said n over there. And then separately, you need the x's. And the power on the 5 at the bottom is the same as the power upstairs. So both good. Where does this one start? 0, 1, 2, 0, because we need the first term to be 1. Okay, so there you go. So that right there is the closed form, the sigma form of that power series. And so let's go ahead and write here number 5. We'll go over to Joe. Okay, so we'll start with x equals 0. If you plug in x equals 0, you are doing summation of what? X is 0, so 0 over 5 to the n, which is really the summation of a whole bunch of zeros. Right, so that is a lot of zeros if, oh, I lied though. All of them are 0 except for which term? The very first term is a 1, so technically 1 plus nothing plus nothing. 1. All right, so we get 1 when we plug in x equals 0. Super. Let's try plugging in x equals 1. So here, so I'm just gonna box this one in red. That's the formula that I'm using every time. So here I'm looking at 1/5 to the n, right? So if I plug in 1 for all those x's in the original, 1 plus a 5th plus a 25th plus dot dot dot. And the question doesn't ask us to do it, but couldn't we figure out what the answer is? It's a geometric series. It's one of the few things we actually know what it adds up to. So the a over 1 minus x, 1 over 1 minus a fifth. So that's 1 over 4 fifths, which is 5 fourths. So when we plug x equals 1 into this function, we get 5 fourths. You used to think that finding values of functions was easy. Plug in the x, you get your answer. It's almost immediate, right? For these functions, you have to do an entire series calculation to find the output. Let's try plugging in x equals -3. So this would be summation of, so again, I'm going back to that red one. So it's -3 over 5 to the n. Let's replace the x with -3. All right, let's write out a few terms. What's the first term? Going back up to the x version. 1, x is -3. So -3 fifths. What's the next term? This x squared over 25. It's a positive 9 over 25. Next one. Minus 27 over 125. And again, what kind of series is that? That's geometric. It is alternating. We can use our geometric series formula to figure out what the answer is. So let's see, again, a over 1 minus x. First term over 1 minus, what's the ratio? It's -3 fifths. So that's going to turn into a plus downstairs. One over 8 fifths, which is 5 eighths. Great. And let's do one last one. We're going to skip E, but let's just do D. So here, going back to the red, summation of, I'm doing D. So 6 over 5 to the n. Right? Replace that x with 6. Now go back to the one where it's written out, x squared, x cubed. So the first term is always 1 plus 6 fifths plus 36 over 25. We'll write one more term plus. Greens are the cubes. 216 over 125. Sam? This one diverges. Don't use that a over 1 minus x. What's the ratio in this case? 6 fifths. Remember, the magic ratio needs to be between -1 and 1 to converge. So this one diverges. Okay, so we've got this really strange formula. It's this infinite polynomial. If I plug in 0, I get 1. I can imagine now plotting points. If I plug in 1, I get 5 fourths. If I plug in -3, I get 5 eighths. If I plug in 6, I get infinity. It diverges. So it's very different from any polynomial we've studied before, because plug 6 into any polynomial and you'll get some number. You won't get diverges. So all right, so let's go to the next page, and we'll answer this question on number 6. Garrett.
For what values of x series 1
Okay, so again, it's a geometric series. So we need to know the common ratio. What's the common ratio in general? 1/5? X over 5, right? That's the thing we multiply by every time. And in order for the series to converge, we need that ratio in absolute value to be less than 1, right? That's the magic number for the geometric series. Okay, so that means that x over 5 must be trapped between what two numbers? -1 and 1. For all the work you did maybe in some previous algebra class solving inequalities, right, finally, a reason to care about solving inequalities. Did take a while, but the payoff is worth it. So what is x between? -5 and 5, right? Multiply all three parts by 5. What's the one funny thing to remember about inequalities when you multiply? Yeah, if you multiply by negative, you change the direction of those inequalities. So multiplying by +5 stays. Okay, so if you plug in any x between -5 and 5, then the infinite series that's up here, the power series, converges. What was the one value of x we plugged in where it didn't converge? It was 6. Make sense? Yeah, 6 is not in this interval. Okay, let's go to number 7, Sam. Okay, so I made this graph in Sketchpad. I'm going to show you just first of all the graph y = 1. What kind of a graph is that? Just the horizontal line. So it's right there at y = 1. Then I'm going to show you 1 plus x over 5, the sum of the first two. What kind of a graph is that? The line going which way? Slightly uphill, so it's that. And then I'm going to show you 1 plus x over 5 plus x squared over 25. What's the name of that graph? It's a parabola. It's going to be opening upwards. It's that one. And I'm going to show you the cubic, the 4th degree, and the 5th degree, and the 6th, 7th, 8th, 9th, 10th. So that last guy is the 10th degree one. And so you can see, even though I would say a 10th degree polynomial and a horizontal line don't have very much in common, there is a natural progression from the first thing to the last thing. I don't think so. Let's go back and take a look at it. There it is right there. Yeah. Okay. So let's get rid of, let's see, I just want to hide them all. And now I'm going to show you this thing. I'm going to compare that to the last thing. So the last guy, the 10th degree polynomial is this. 10th degree, does it make sense it went up on both sides? Yes. And then I'm going to show you this blue thing, which is this guy. What is that? David. Yeah. We know a over 1 minus x is the infinite sum formula. So again, what's the first term? It's 1, and what's the common ratio? X over 5, and 1 over 1 minus x over 5 is this guy, which looks nothing at all like a polynomial, right? All the other ones I showed you were polynomials. But do you see that the 10th degree one looks an awful lot like this blue one between -5 and 5? I'm sorry the numbers are so small, but that's -5 and that's +5 out here. And -5 to 5 is what we said for where the power series converged. So if you are between -5 and 5, then all of these polynomials, here's the last one, get closer and closer to this blue function right here. And if you are outside of this interval, -5 to 5, then all bets are off. The series diverges, even though the blue function exists perfectly well. Okay, so what I showed you, the little teaser I showed you at the start of class today, I gave you a bunch of terms that look like they were doing, look like what function for a while, looked like sine graph, but then it stopped looking like the sine graph at some point. So it's the same idea there, where we're doing polynomials and making it look like something that is decidedly not a polynomial. Okay, so let's come back here and we're going to take a look at number 8. Says we're going to look at this power series here, x minus 2 minus x minus 2 squared over 4 plus x minus 2 cubed over 9 minus etc. So first of all, do you guys remember on the previous page there was this thing that we called a in the very first definition of power series? What is the a in this problem? It is 2. Make sure you recognize it's always x minus a. There's a minus sign built in there. So you change the sign of whatever is in there to grab the number a. Okay, so the a is equal to 2 in this case. Is this one here a geometric series? Yeah, the top part, what do you multiply the top by every time? Like if you're sitting at x minus 2 cubed and you want to get to x minus 2 to the 4th, you multiply by x minus 2. We could handle the alternating parts by multiplying by a -1. Is the bottom part this same constant multiple idea? 4 to 9 to 16? Those are the squares. They're not constant multiples of each other. So this is not a geometric series. So we can't do the nice thing that we did last time with our geometric series. You know, it converges whenever the ratio is between -1 and 1. So in order to figure out where this thing converges, because this converges for some values of x and diverges for others, and in order to figure out which are the good x's, the convergent x's, and which are the bad ones, the divergent x's, we need to first write the series in closed form with summation. And this problem that we're about to do, this whole problem here, is essentially what I'm going to ask you to do 4 times on the project. So let's see if we can do this one together. All right, first thing we need is to write the series in closed form. So we start with a summation. Our job as detectives here is to try to come up with a general formula for each term. So first of all, what's the same on the top every time? Is an x minus 2. And then the x minus 2 is getting raised to different powers, so it feels like that's where we should stick the n. Okay. And now our job is to figure out what's going on at the bottom. So David recognized these are the squares. The question is it n squared? Because we have to really make sure that the n we use upstairs is the same n that we use downstairs. So when n is 2, what number is living downstairs? 2 squared, that's nice. When n is 3, it's 3 squared. Okay, super. So it's exactly n squared. So downstairs we're going to put n squared. What other thing do we have to take care of in the terms there? Is the -1. So for me, my default thing to put here every time is -1 to the n. And if I get it wrong, then I'll change it to n plus 1. It's easy enough to do. X not equal to 2. Where do you see a condition like that? 0 upstairs is okay. 0 downstairs would be bad. Yeah, 0 upstairs is all right. Okay, let's look at the starting value of n. Let's see. So the first term here is x minus 2 to what power? To the 1. So that had better be n equals 1 as our starting thing, right? 1 to infinity. Everybody see where we got that 1? Yeah, then now finally I'm ready to look at that -1 part and decide if it's right or not. So if you plug in n equals 1, is that -1 positive or negative? It's negative, but the first term was supposed to be positive. So then we'll fix that. Of course, I didn't leave enough room to fix that, but let's see if we can fix that. So maybe -1 to the n plus 1. And that's just going to take all the alternating signs and shove them over one spot, which is exactly what I want.
Well, in this case, it really doesn't even matter as long as you add an odd, right?
As long as you add an odd, yes, any odd number up there, n plus any odd number is good. But my two defaults for alternating series are always either -1 to the n, which didn't work, or -1 to the n plus 1, which does. It's going to be one of those two. So you just have to pick the right one. So any questions on how we came up with all the different parts here? Okay. So next thing we're going to do is try to decide again what the good x's are, the x's where that series converges, and what the bad x's are, the ones where this series diverges. And we have an, what do we have here? We have a power function upstairs, right? X to the n, and then downstairs, sorry, didn't say that right. If you plug in a particular number for x, what kind of a thing is this? It's a number to the n. If we're plugging in a particular number for x, a function of the form a number to the variable is an exponential, right? So I got a little confused there. I looked at x as the variable, but x is going to be, we're going to plug numbers in for x. N is the variable for this series. So that's an exponential. Downstairs is a power, n squared. And when you have exponentials and powers mixed together, the ratio test is often the way to go. So we're going to use the ratio test here. And we're going to use the ratio test on every problem like this, including the 4 on your project. The ratio test is the most important of the tests that we studied because it opens the door to power series. So the goal is to figure out when this thing converges, and we do it with the ratio test. So let's see if we remember the ratio test. Limit as n goes to infinity. We're doing a fraction. Yeah, what's the order? Where does the original, yeah, so the original guy, the general guy goes downstairs, and then the n plus 1 guy goes upstairs. And then absolute value. And when we did these problems on the ratio test day a couple of days ago, the absolute value played no role. Here it plays a big role. We need it. Okay, so let's plug in. Limit as n goes to infinity. So the easiest thing to do is start on the bottom. You just copy the whole term that's in purple there. -1 to the n plus 1, x minus 2 to the n, divide n squared. To figure out what goes upstairs, all the n's become n plus 1s. -1 to the, yeah, that n becomes n plus 1. This n becomes n plus 1, plus another 1 is n plus 2. This guy becomes x minus 2 to the n plus 1, divide by, used to be n squared, now it's n plus 1 squared. Every n becomes n plus 1. And of course, absolute value around the whole thing. All right, so we're going to do some algebra on this, and it looks a little bit frightening, but you guys have a lot of experience now with handling fractions within fractions, so that's what we're going to do here. I'm still copying the limit, and is going to infinity at the end of this problem. Okay, so I'm going to copy the x minus 2 to the n plus 1 divided by the n plus 1 squared. But then this is the trick where we change division to multiplication. And what do we do with the bottom fraction? Flip it. So n squared over x minus 2 to the n. Still absolute value. Didn't I write? It's the -1s. Because in my mind, I'm taking the absolute value of them and getting 1. So I'm free to not write them anymore. And it's also true that the n squared terms are positive, right? N is positive. but the x could be a negative number. So we really do need the absolute value because there's x's floating around, and we don't know if the x is positive or negative. Okay, now we need to start simplifying. So I'm going to split my fraction up. I'm going to split these two fractions differently. I'm going to split the x parts from the n parts. So over here, x minus 2 to the n plus 1 over x minus 2 to the n. And then the other fraction will have the squared things. What happens with those x minus 2's? Yeah, most of them cancel. We will have how many left over? Just a single one, and where will it be? Up on top. So upstairs is just x minus 2. Okay, downstairs, for the n part, I'm just going to copy. I'm going to go ahead and square the bottom thing. You don't technically need to write it out, but I just want to really be clear on this limit that we're about to do. With respect to this limit, what's the variable? Is n, which means that that x minus 2 is what kind of a thing? It's constant. And constant multiples inside of limits can come right out in the front. And so that x minus 2 goes right in the front. What am I missing around the x minus 2? Yeah, I mean, like at the very least, it needs to be in parentheses, but it actually needs to be an absolute value because it was inside of the absolute value before, so it's still in the absolute value. It's constant, it comes to the front, but it might have been negative, so we need to keep it in the absolute value. I'll put a dot for times there. Okay, and now finally we get to the limit, and I'm really hoping that we can find this limit without breaking a sweat. What is this limit? It's 1. Again, the powers are the same, right? So when the powers are the same, it's just the numbers in the front. 1 over 1 is just 1. So that limit is 1. So what we are doing is plugging in really big numbers for n. And we are saying that when n is huge, the thing on the bottom that dominates is the n squared. So I don't even see that anymore. It's not that it's left over there to cancel. You just completely ignore it because it is dwarfed by the n squared in the front. Okay, so then when all is said and done, this limit is absolute value of x minus 2. Okay, now remember, what test have we been trying to do this whole time here? That's the ratio test. What's the magic number for the ratio test? It's 1. I'll put it in a different color here. Do you need the limit there to be more or less than 1 if you want to converge? It's less than 1. That is the ratio test. So in order to make sure that the original power series converges, we need to make sure we pick x's so that absolute value x minus 2 is smaller than 1. So again, more practice with inequalities that you did many years ago. X minus 2 is therefore trapped between what two numbers? 1 and negative 1, right? It's inside of absolute value. Are people clear on that step? Again, absolute value is one of these things that you play around with a little bit in an algebra class, and then you don't do anything with it for like 3 semesters, and here we are dealing with absolute value inequalities. We're gonna solve for x. How do we solve for x here? is you add 2 to all three sides. Right, so let's add 2 to everything. And we get 1 less than x less than 3. So if you pick x's between 1 and 3, the original power series will converge. Either one. Yeah, when you multiply or divide by a negative is when you change that direction. Any questions on this? All right, I hope there's a little bit of room left on your paper. There's not much left on mine here. But every time we do the ratio test with power series, we need to take a look at the endpoints separately. If you plug in x equals 3, what do you get in here? When you plug in x equals 3, you get 1. What does the ratio test say when the limit is actually equal to 1? Converge? Diverge? It's inconclusive. It's not any kind of news, actually. So x equals 3, I don't know what the answer is. If I plug in x equals 5, what do you get here when you plug in x equals 5? It's 3. That's definitely not less than 1. So when you plug x equals 5 in, it certainly diverges. But when you plug in x equals 3, the test is inconclusive. So we need to do 3 separately. And we also need to do 1 separately. When you plug 1 in here, you get -1, but it's in absolute value, so it becomes +1, which is that dreaded number that is inconclusive. So you always have to do the endpoint separately when you're doing this ratio test here. So let's check the endpoints. So we'll start with x equals 3. Go all the way back up to the original series. And we're going to plug in x equals 3 for all of these x's here. What do you get in every parentheses? We get 1, yeah? When x is 3, every set of parentheses becomes 1. So I'm just going to write out the first few terms. Every parentheses becomes a 1. 1 minus 1/4 plus 1/9 minus 1/16. Everybody see where that came from? And that's a full-fledged series that we need to decide, does it converge or diverge? Before we do, let's just plug in x equals 1 as well. Remember the 2 endpoints we have to check separately. So all the x's are going to become 1s. What's in every parentheses when x is 1? Is a -1. So let's see what happens. Every parentheses becomes -1. So the first term is -1. This guy is a -1 squared, which becomes +1, and it's subtracted. So that's also going to be minus. This is -1 cubed, which is really -1 with a plus sign. So that one's minus. Do you see that they're all minus so far? We'll do one more. X is -1. Sorry, this parentheses is -1 to the 4th power. +1, but it's being subtracted. So every one of these terms is minus when all is said and done. You can write out the details if you want to see more of them. But just very carefully plug in x equals 1 everywhere. And I will write what we get. -1 minus 1/4 minus 1/9 minus 1/16 minus ... Okay, what kind of test for the first one, the x equals 3 one? Maybe the alternating series test. So we're not going to write out all the details here, but just the highlights. For an alternating series, we need the thing to alternate, check. We need the terms to be decreasing. Are the terms decreasing? Yeah, so we'll write that. Let's see, so terms decreasing. That's that one. And we need the terms to go to what magic number? 0. And do the terms in this one go to 0? Yes. Check. So by the alternating series test, it has only one conclusion. What's the conclusion of the alternating series test? It converges. The series converges. I said I would never just write the series, but I'm hoping it's clear we're referring to that row. That's the only series we're talking about here. Okay, next one. -1, -1/4, -1/9, -1/16. Can't use the alternating series test. Anybody recognize that series? It is a p-series. This is equal to, I'm going to put the negative in the front, and then I'm just going to write the formula. Aren't these guys all 1/n²? Yeah. And so we know this p-series, let's see, p-series with p equal to 2, technically it's the negative of a p-series. So p-series p equal to 2, which is bigger than 1. So what does that series do? So the series converges. And so the series converges at x equals 3 and also at x equals 1. And we're done. I'll highlight, Garrett said something real good. What did you say about that bottom series?
That's absolutely.
Yeah. So we saw that the sum of 1/n² is absolutely convergent, meaning it converges on its own, and therefore automatically is going to converge where we alternate signs. So if we had done the bottom one first, we might have saved a little bit of time and gotten the top one for free. I don't know, it's a little bit more efficient. I wouldn't worry about that detail unless you're really comfortable with the concept of absolute convergence. But the series converges for both endpoints. So the IOC interval of convergence for the original series. So we've already decided it's all the x's between 1 and 3. That's right. And with all this work, we decided at those two endpoints it converges. Okay, real common to use interval notation for interval of convergence. Exactly, you leave the equal sign off if it came up divergent on one side. Okay, so I do have a sketchpad thing we can take a quick look at for this one. Let's see if we can find it, 95B. Okay, here's the series in question, right? So what did we decide the interval of convergence was? From 1 to 3. So between 1 and 3, which is where that thick black line is there, we're expecting the series is going to do nice things. Outside of that, all bets are off. Note that there's a big dot there in the middle at x equals 2. X equals 2 is this value of a, right? And that's called the center of the series. And so we'll show you just x minus 2, which is that line, then the parabola, cubic, fourth, fifth, sixth, 7, 8, 9, 10, and then finally an 11th degree polynomial. Do you see that these things are kind of honing in on something between 1 and 3? Yeah, and so this guy converges for all numbers between 1 and 3. All right, a little bit of vocabulary, and then we'll do some group stuff. Okay, we'll go to 9, Bubba. Okay, thank you. So, so for this, the first one we did today here near the green, how much was the a? Because it's supposed to be x minus a every time. It was 0. And the interval of convergence for this one turned out to be all the numbers between -5 and 5. What's the center of that interval? 0. No surprise. It's the same as that value of a. What's the a value in this series? Is 2. what number is sitting right in the middle of 1 and 3 is 2. So it's called the center of the series. It's always the center of the interval. And so the distance between the center and the end is called the radius. So for the first series, it was minus 5 to 5. And for the second one, the interval of convergence was 1 to 3. And so the radius in the first one, how far is it from the center of that interval to the end? It's 5. Yeah, it makes no difference. Yeah, it doesn't matter whether the endpoints are included or not. And then how far is the end of this 1, 3 from the center? Is 1. That's the radius. From the center at 2, you go 1 in either direction. Questions on the radius? And on the project, I'm going to ask you guys to find the intervals of convergence and the radius of convergence. Okay, so last part here. 3 possibilities for a power series about x equals a. It is possible that a series converges only when x equals a, and not for any other number, so you don't even get an interval. What would you guess is the radius if you only converge at a single point? Is 0. And the interval of convergence is not actually an interval, it's just the single point. So just the number a, if you want to be fancy, use the curly braces. I just am deficient on the right-hand side of the curly braces. Okay, part B. There could be a very well-behaved series that converges for all real numbers. What would you say is the radius of that series? Infinity. It goes forever. And the interval of convergence, all real numbers, that's what it says. So you could say minus infinity to infinity, or you can write the fancy R. In the 2 cases that we saw, the radius was some finite number. First it was 5, then it was 1, not 0. Okay, so in this case, r equals, and I don't want to give it another name, we'll just call it r, but then we can write something for the interval of convergence. What's the center? What's the letter we said? For the center is a, which means that the interval of convergence, well, it's kind of a on both sides. Yeah, a minus r, like go r to the left, and then a plus r, go r to the right. Right, so that's how we center it at a, and then you go r in either direction. I've put parentheses like it's not including the endpoints. It depends on the particular series. So those could be closed brackets or one of each. Okay, so this isn't laid out as a group thing, and I don't even think I have an answer key for these, but let's see if we can get answers to these. So your job is to do a bunch of things for these series here, and again, this will help you quite a bit on the project. You're going to write each power series in closed form, meaning with a sigma. Then once you have the sigma, that opens the door to the ratio test. You do the big ratio test calculation. You'll get some interval. What do you have to check separately? Is the endpoints of that interval. So that's the goal. So let's see if we can help each other out. I'll walk around and take questions. And once we get answers, maybe we'll put them up on the boards. Start at part A. It goes on to the next page.